Welcome back. This is the Tutor Wizard. Please subscribe here to get more videos. Well, I'll harass you at the end of the video too. What we're going to do today is explain what n-gons and n-grams are. Basically, I've been posting a bunch of these pretty pictures on Facebook and Twitter. And so now I'm going to explain how we can draw these and do a little bit of graph theory here and there. I'm going to throw out some terminology about graph theory. If you know what graph theory is and you've taken this, then you can pay attention to what K12 is. I'll explain it quickly what it is. It's not that bad. And then we're going to get a little bit of mathematical notation for what these grams are. So the most famous gram I'm pretty sure is Instagram. Okay, yes, you're right. But after that, it's the pentagram. The pentagram is the one that you probably know the best. And Instagram. I will start posting on Instagram immediately. I'll post a pentagram on Instagram after I get a razor. Magic razor. So this is, before I erase the pretty picture, like, no, I'm going to. Before I do that, I'm going to drink some coffee. And then I'm going to explain what this guy is. In graph theory, what this is called the K12. What's K12? I'm going to guess because they were using German, so they didn't use the C, they used the K. But it's the complete graph. If you don't want to know what the complete graph is, basically what that says is you take, it was 12. Why? Because I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I just force you to watch me count to 12 also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't know if I have to pay for that jingle now. Open domain. I don't know. So I have 12 vertices, so we call it K12. And why is it complete? It's the most connected simply, whatever that means. So you have to use straight lines, and you can't use more than one line connecting them before. So I used the circle originally, and I had to erase it. Otherwise, it would have had multi-edges, and we don't want that. So the complete graph on 12 vertices means you have 12 vertices. And then this is coincidentally how you would start describing how disease is spreading through 12 cities. You have different connections between all the cities, and then you want to see how that disease is spreading through. So we would look at and describe the complete graph. We're going to actually start talking about graphs in these models eventually. We're going to do where we mathematically model where we have a bunch of cities, and then we want to see how to completely connect everybody. That is K4. So what do we mean? You take 3 vertices. Every vertex has to be connected to every other vertex. Bang, bang, bang. This is K3. This is K4, who is also the tetrahedron. You're like, what? Yeah, no, that's not what you do. You can't just make the vertex here. So how is this the tetrahedron? Oh, I just move it slightly. How did I do that? I move this vertex here, and then you pull it out of this, and then you get... So this guy is the tetrahedron projected into the plane. Either way, K4 tangent. I don't want to view it that way, so don't worry. We're not going to do graph theory or the complete graph. I just wanted to show you that essentially doing all these n-grams, if you do them from 1 to half of the number, essentially, depending on whether they're odd or even, we'll get into it. You can systematically build Kn from doing all the n-gons and n-grams. So what do we want to talk about today? We don't want to talk about too much graph theory. I just had to point out that it will complete a complete graph or construct a complete graph if you do them all in the pretty colors. What's an n-gon? The n-gon is the blue one. So here we go. Nothing lasts forever. Nothing lasts forever. Even corona isolation. Nothing lasts forever. What do I do with this now? This is the n-gon. The n-gon, or the regular n-gon. Mine's not regular because I didn't actually map out. I just grabbed 12 vertices and put them up there. And 12 is kind of poo because it's even and it's not an odd number or a prime. So with most of the other ones you're going to see me do today are going to be, well, no. Actually, when you do even numbers and then numbers which are relatively prime to that, what does that mean? Their greatest common divisor is 1. They have nothing in common. Then you get nice stars from this. What is the gram? So an n-gon is just you connect every adjacent vertex to each other. Let me back up a little bit. First, what you do is you take a circle, then you evenly space out the points. If I want to do 4 grams, you're only going to get fancy. You can do blah, blah, or you can do da, 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 da. And then if you erase them, oh, look what I got, K4. From doing all the grams. This is what I was talking about, where we're going to build them. Continuing on, that means that the 12 gon is the regular 12-sided object, which you obtain by evenly spacing out 12 points on a circle and then connecting all of the 12. 1 means I'm going to connect every vertex that is directly next to it. I don't skip any, I just skip to the next one. So I skip to the next one, skip to the next one, skip to the next one. How many times will I say skip to the next one? There. I have the n gone. That's actually not, and I'm pretty sure you've probably heard of those ones. This is what they used over history. The Greeks and a bunch of other people have systematically tried to use to approximate the value of pi by inscribing and subscribing circles in regular n-gons, and then you get better and better approximations to what the length of the circle is and therefore what pi is. So I'm pretty sure you've seen what an n-gon is. What's the regular pentagon? The housey guy. And then there's the favorite one that I was talking about, who's the pentagram. What's the difference between the gon? The gram now is the famous star that you've been so used to building. It's this guy, the star. So just to recap one more time, the guy that we're not going to talk about too much is the regular n-gon, or the square. He doesn't have an on there, but then the pentagon and the hexagon and the septagon, or the heptagon, if we're going to keep going in there. Septa, hepta. Who's which one? Greek and someone else? I don't really know. I don't know everything. I've been told I don't know everything. I guess. I like to think it's tending towards infinity as time progresses. It's a limits scenario. What is the regular n-gon? The regular n-gon connects. So here's what in rhetoric, what have I tried to say here? It connects adjacent points in an array. So you skip you go to the next one. So it's the way we're going to call it the n1. So the n1 gram is actually, the n1 gram, we're going to call it, is actually the regular n-gon, what they call the n-sided object. Where's n-gon? Right here. Right here. So I connect adjacent ones, and you get, if I have 5 of them, sure enough, I get a regular, or mine wasn't too regular, but you get a pentagon. And then what I was saying earlier, then I erase the ambient circle that we started with, because now I have the 5 points fixed. And if you want to start drawing the star from that, you need another color. If you want to start drawing the star in there, or the pentagram, the one that everyone knows and has a name, and then we're going to generalize the gram scenario. I join not every adjacent one, I join every second one, and then you get the star. Someone squished the regular gon. So this is the difference between the pentagon and the pentagram for this one, because, and now we're going to start getting all the mathy. It's not too bad. 5 is 2 times 2 plus 1 is 5. You're like, why does that matter? Because the 5 doesn't interest me. Sometimes the arithmetic, or whether he's odd or even, is important. Because of that, this is what we're going to notice, is that there's going to be if we're going to say if n is odd, 2k plus 1, then there are exactly k, where you have n is 2k plus 1, there will be exactly k edge distinct Hamiltonian cycles in the complete graph. This is k5 because we have 5 points. What am I saying here? I'm talking about a little bit of graph theory now again. What that says is I know this one, and historically there could only ever be with 5 points the pentagon and the pentagram, because the 5, if I put 5 in here, the 5-1 is going to be equal to the 5-4 gram. If I skip 4 points, where would I go? 1, 2, 3, 4. I would still be joining this one, and then these ones would join. And then you would just join it the other way, essentially. So the 5-1 and the 5-4 gram are the same. And then the 5-2 and the 5-3 gram are going to be the same. And then the 5-none gram, you can't do the 5-5 gram. Where am I joining? You're joining these. So there could only ever be, with 5 points, the pentagon and the pentagram. And coincidentally, quickly, if you have taken some graph theory, cleverly what Peterson did was he took the pentagon and then he took the pentagram and then he just joined them, and this is called the Peterson graph, and it's 3 regular. Every vertex has degree 3, and it's all kinds of nasty non-planar, non-Hamiltonian business. Take some graph theory, watch the videos, there will be links. All right, now What is this going to be about? This one's going to be about the regular ngrams. How do we create these? Again, what I'm going to do is I will create, what's a number we want? Someone shout out a number between 1 and 10.
7.
7. That's the most common response to pick a number between 1 and 10. Now he's going to make me draw the 7 gram. And let's try and make it like the one on Danny. So we're going to do Danny Carey from Tool's drum kit. He has the 7.2 gram, I think, or the 7.3 gram. We'll find out which one. You can tell me, comment below which one it is. What he does is he's got 1, 2, now I'm just eyeing it. 3, 4, 5, 6, 7. I used a circle and then I used a compass and then I did some math. No, I didn't. I just eyeballed it. So there, I have those guys. Coincidentally, if I do the 7 gram, or the 7 gone, sorry, I'm going to get this. That was not so bad. It's a fairly good regular 7 gone. This is the 7.1 gram, which is also equal to the 7.6 gram. Now we need some more colors. I'll drink my coffee. I don't think I need that many, but just in case, I got colors. Colors. We got all the colors. We're gonna rainbow drop. Just a second. Whoa, preemptive rainbow dropped. No rogue drops. Now let's do some of the other grams. Which one do we want? 7.2. I think it's the 7.3, but we're gonna do them all anyways. So now what I'm gonna do is I skip every second one. Let's skip, and then it reconnects. There's one. It's not that one he uses. He's using the 7.3. Let's draw that one. What do we want it in? Hot pink, green, purple, green. What do? We skip 2, so now we're going to skip 3. So what I do is I start with 1, and then 1, 2, 3. 1, 2, 3. This one gets it. That's definitely the one that he's using. 1, 2, 3. 1, 2, 3. This guy. 3, 1, 2, 3. This guy. 1, 2, 3. Now that guy gets it. And then 1, 2, 3. There's the one Danny Carey's using. Who is that one? So the blue one is the 7.2 gram. Or the heptagram. I don't know which one is going to be now. See, the pentagram got its name because they didn't have to worry about it because there was no other choices, because the 5 was the smallest number where you're going to get fancy ones. See, in 3 points, the only one you're going to get is the regular trigon, which we call a triangle. Trigonom is the measurement of 3-sided objects, trigonometry. So you get trigonomes if you only have 3. If you have 4, he's not odd, but you get a square. You can do 4 2 grams, which are straight lines, and then you get K4. And you get K3. To do now K5, we saw 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, you get that, and then 1, 2, 3, 4, 5. There, now you get K5. There was only 2 of them, that's why I got a name, pentagram. And then mathematicians somewhere along the line went, oh, you could do that for all kinds, and then here's the one, let's do it in blue. Here's the next story. 2, 3, 4. No, I always want to do 5. It should be the hexagon. If I have the regular hexagon now, what am I going to get? Guesses? If I skip one now, and then I'll point this out, we're going to get, if I skip them, oh, I didn't do the weird magic. It didn't go all the way around and make nice stars like this when it disconnected. So I'll just move around and then do one more, and Star of David. So the Star of David, they were just playing the same game as this one, and then I could get another one. Is there another one in there? Let's try. Color. I used blue already, green. And then what if I skip 3? Yes. But those are the only options. There's no other star that you can create from that. You're going to create the 6-1, which is, or 6-2, which is just going to be 3 sets of lines. Or you can do the 6-2 one, which is going to be 2 interlocking triangles. Or you can do the skip 1, and you're going to get the hexagon. So you get the hexagon, the 6-2 gram, or what they call the Star of David now. Or you can have the lines in there, and then this would be, do I get that 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Once the degrees all have 5, this is K6 now. So this is how you complete, and that's why I want to talk a little bit about graph theory. This is how you can systematically build from these grams, these guys. The other thing, while I've got it and it's in my mind right now, the whole point of that rant was to get the stars that are nice and connect back with each other. The n, the number of vertices you have, in this case 7, And the gram that you're trying to create, the 2, the K, they have to be relatively prime. What does that mean? The greatest common divisor has to be 1. You're like, your explanation to the first definition didn't help me any, because I don't know what greatest common divisor equals 1 means. That means that they have no numbers in common. All prime numbers are relatively prime to everybody else. So if you pick a prime number, it's always going to work where you get fancy ones. Here, when I did it, the Star of David got 2 triangles which disconnected because 6 and 2 have a greatest common divisor of 2. 2 divides 2 and 2 divides 6. So it's not a 1. So you get where they don't interlock. We'll do it again in the examples to see. But who's the last one we could do in this one, probably, to create one more? We did, what did we just do? Or is this 1, 2, 3, 4, 5, 6? Oh, look. This is K7. So you can systematically create K3, K4, K5, K6, K7. I just did it. I didn't even plan that out. This is how you build the complete graph on n vertices, is with ngrams and n-gons. Let's do it a couple more times. We'll draw a couple pretty pictures and then we're done. So let's do 8 and we'll draw the magic ones first. I like to draw the 8-gon or the hexagon. No, hex says 6. Octa 8. That's confusing in music too, because it's, why is the octave only 6 steps? Math is hard. So here's the octagon, the stop sign. I should have done it in red. It's too late. We're not going back. Now to get fancy ones, hopefully I didn't remove clarity and I added some. Here n is 8. And I want to look at now how many grams can we do. I just did the 8 1 gram, which is the octagon, and that's going to equal the 8 7 gram quickly. Theorem, I'm not proving it, I'll just state it. You guys can prove it, post it in the comments below or try and show me. If you have n, k is equal to n minus k, or k equals 1 to the floor of n over 2. I'm not telling you what the floor is either. People start explaining these things to each other in the comments. That's the whole point. Math is awesome. So I have a theorem where these guys are equal to each other so I can go back and forth. You can see intuitively, if I'm going to do 1 and 7, why is this true? You can see it right now. If I start here and I fix this guy, let's fix our starting point right now anyways. If I fix that starting point, that's where I'm going to start every time I try to make these n grams. In this case, 8 grams. For the 8-gon or the octagon, I'm just going to join the next one. And then that would take me going clockwise, or anti-Greek-wise, I like to call it, clockwise, right? And then what we're going to do is, if I did 7, if I skip 7, count it, 1, 2, 3, 4, 5, 6, 7, I would join these ones. But either way, this edge would get built instead of this edge. So if you went around the 8, 7 is going to skip 7, but eventually it's going to draw all the outside ones. It's going to draw the same thing. And that's why they're the same. And then now, that's why I'm going down the list. Now I'm going to do 8, 2, or that should be equal to 8, 6. 8 minus 2. 2 and 8 are not relatively prime. The greatest common divisor, 8, is 2 times 4 plus 0. So 2 divides 2. I know, the horrible cutty cut. Why did they make that symbol? They had 8 things. And they want to cut it into 2 things. Oh, cut. So 2 cuts 2 into even pieces. And 2 also cuts 8 or divides 8 into even pieces. So the GCD, we call it, of 2 and 8 is 2, which is strictly larger than 1. So I know that it's not going to connect back on itself. It's going to create 2 interlocking 8 divided by 2-sided gons. It's going to create 2 squares inside each other. Circle gets the square. Who gets the square? Red gets the square. Red gets the square. 2 of them. So if I skip every second one, 1, 2, 3, 4, I can cheat and not even have to pay attention because I knew there's the first square, and then the other one, if I move to this point, it will create the interlocking square. Square. Who are those ones? Red is the 8, 2, which also equals the 8, 6 gram. Finally, who's going to get it? Green, I'm going to guess. Because what does that say now? 8, 3 will equal 8, 5 grams. And then we can use orange for the 8, 4 gram. He's actually equal to 8 minus 4 is the, when you're in even, you're going to get the 8, 4 equals 8, 4. When you get odd, you're going to get, haha, you can leave out the extra one. You'll see I'm going to do an odd one next. I don't like 9 because 9 isn't actually a prime number, so poop on 9. 9ers out. 11 is what we're going to try for. I tried to do 11 at the beginning and I can't count and I got 12, so I just stuck with it. Math is hard. 8, 3. I'm going to skip 3. I know. Start here. 1, 2, 3. Skip. For some reason, drawing these is easier over here. So 1, 2, 3. Skip. 1, 2, 3. Skip. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. And then 1, 2, 3 back to where I started from, and it linked up. Do you see that time when I did that? It linked up to itself. And what's the difference? Well, 8 and 3 are relatively prime. 3 is prime and 8 is 2 cubed. They're relatively prime. And so it does link back on itself. Their GCD is 1. Now what's the last one we're going to do? I said I would use orange. What do we have to connect? Every 4, which is the antipodal ones, especially in a nice even 8-sided thing where we have nice symmetry. What this 8 4s are going to create is 4 disjointed 2 grams, or line segments between 2 points, antipodal points. So what do I mean by that? The antipode, the one standing opposite in the circle, join. Oh, that wasn't very nice. Now he's going to be off of where they're supposed to intersect, and I'll fix it, watch. Now these ones, antipodal, join, antipodal, join, antipodal, join. And those weren't supposed to be a whole. They're concurrent, actually, if you do this create. What's concurrent? Watch a video on Euclidean geometry. We're going to get Mark Solomonovich in here, and we're going to do a bunch of Euclidean geometry videos too. He's a wizard. I learned from a better wizard than me. I just turned to the dark side. To finish off, let's do the 11 grams. So 11K. 11 this time now is both odd and prime, so it's going to do something magical. It's going to give me, let me write out the math. 11 is 2 times 5 plus 1. There should be exactly 5 edge disjoint Hamiltonian cycles in K11. What? I'm going to draw 5 fancy stars in K11 now, and the 4 fancy stars, and the N gone, the 11 gone. So here's the 11 gone. Now what do I want? 11, 2. We just did 11, 1, which is equal to 11, 10. Next, red. We need to do now 11, 2, which would be just like the pentagon, because it was the 5, 2 is the pentagon. So this is going to look like the pentagon type of star. But that's the 11, 2, which will also be the 11, 9. It's much faster skipping 2 than skipping 9 every time. Why are you doing that? Skip 2. Here's where I start every time. Skip 2, 1, 2, skip 2, 1, 2, skip 2. I almost have to say it out loud, otherwise my brain's like, no, skip this many. Now, do you see, it won't come back on itself. There's 11, it's going to start interlocking, which is really cool. And then it's going to do this, and this, and this, and this. And then it comes back to where I started. There's the 11, 2 and the 11, 9 grams. You're done too. Why is there 2 of them? Get out of here. Green. Now we're going to do the 11, 3. He's jumping the gun anyways, and that's going to be equal to the 11, 8 grams. Now I skip every 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Now it's going to start interlocking. 1, 2, 3. Now it'll start interlocking again. 1, 2, 3. Interlock, interlock one more time, and then come back to where I started from. There's the 11, 3 and the 11, 8 gram. And I don't know, we got lime green. I bet you lime green's a dud. Anyways, you're double dead. Now what do we got? Orange. Orange is going to be 11, 4, and that's going to be 11, 7, 11 in reverse. These are the grams. What are we going to get? Now I'm going to skip 4, starting from here. 1, 2, 3, 4. We're going to join this one. Then this is the cool one. When you start getting close to the halfway point, those are the really pointy stars. The 5 and the 2 gives you a really cool pentagram because they're close to each other. The midpoint, the 2 is the midpoint. Bang. Now I stop and you're like, what were you counting? Son of a 4. 1, 2, 3, 4. It's already interlocking. 1, 2, 3, 4. this one, this one, this one, this one. Yeah, my students have to watch me do this too. You got no choice. I'm driving. I got the microphone. We're strapped in. 1, 2, 3, 4 should come back there. Now we have the 11 fours. Orange is done. Now what can we do? Hot pink. 11 5, which is equal to 11 6. See, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got them all. There they are. For odd ones, the 4 becomes 4 equals 4, and you only have to do one, and they connect just the straight line segments. Now what are we going to do? 11 5 is going to, I don't need you either. Keep stepping on markers now. I'm going to skip 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, he's the 11 5 is the really pointy one because they're close together. 5 is the halfway point. So if you want the really fancy, cool, demon-looking point, you want to do the 11 or the N halfway guy. That's the one, except it has to be odd. And then that'll give you the fancy one. Shut up and draw. Okay. 1, 2, 3, 4, 5. Oh, he's going rogue. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There to here, then to here, then to here. Who's that guy? That is, we just systematically built using the 11 k-grams of 11 1, 11 2, 11 3, 11 4, 11 5, using those grams, which we call 11k, the 11 k-grams. Create the complete graph K11, which is 10 regular, which has 5 edge disjoint Hamiltonian cycles, each one represented a different color. These are ngons and ngrams. Please subscribe right here. Follow me on Facebook at Adrian the Tutor or at Twitter at Tutor_Inc. I will see you next time. Rainbow drop. There's a difference between regular people and mathematicians. You think that I'm not magically not ever making mistakes. No, if I make a mistake, I just try it again and keep redoing it. Oh, the cat, like meow 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 meow. It's like, is that recording?